So in our previous lecture, we talked about Mason's gain formula, and there we learned how to obtain the transfer function of systems that are represented by block diagrams after converting them into signal flow graphs. And from those signal flow graphs, we learned how to obtain transfer function using Mason's gain formula. And because there are some thing associated with Mason's gain formula that are a bit difficult to understand, so I decided to do a sort of tutorial and try to solve a few more examples today. So I'll again be solving few examples related to Mason's gain formula. So this is a problem where you are given an SFG having multiple loops. So it is desired to find the transfer function of the given SFG. Now, what Mason's gain formula says that if you remember the formula, it comprises of terms like tk and delta k. So the transfer function using Mason's gain formula was given by the expression summation n from 1 to k. Then you had tk delta k upon delta. So this is Mason's gain formula, where k was the number of forward paths in the SFG, while tk is the gain of the kth forward path, and delta was obtained by a formula that we studied yesterday. So we'll try to use the same formula today again. And if in this case, if you see, you have how many number of forward paths? So if you look into this figure, you'll find that there are 4 forward paths which I observe. So one of which is starting from input ending to output. In this direction is G1, G2. So this becomes the first forward path. So I write this. So the first forward path is G1, G2. The second forward path that I observe in this case is G7, G8. The third forward path that I observe is G1, G5. So it goes like this: G1, G5, G8. So the third forward path is to be G1, G5, and G8. And the fourth forward path will be G7, G6, G2. So it's given by this expression, G7, G6, G2. So apart from these 4 forward paths, I don't see any other one. So now we'll talk about loops. So if you observe this particular SFG, you'll find there are multiple loops. For example, 3 loops are straightforward, so you can look at this circular loop, which is G9. So the first loop comes out to be G9. The second loop is G6, G5. So this becomes the second loop. Third loop is G3. The fourth loop comes out to be G7, G8, and G4. So you start from this point, move in the direction of branch arrows. So you end to this point again, and thus G7, G8, G5, G4 qualifies as a loop. Again, you have the fifth loop, which is G1, G2, G4. And then the sixth loop. So can anyone mention what the sixth loop is? What is the sixth loop here? Any answer from your side for sixth loop? So I have written 5 loops on the right side, but there are 2 more loops remaining. So I need answer from your side. No one? So the sixth loop is G7, G6, G2, and G4. So it's G7, G6, G2, G4, and the seventh loop is G1, G5, G8, G4. So you start from this point, move in the direction of branch arrows. And remember, you are bound not to traverse any node twice, which means that if you are going to move in the direction of branch arrows, you will be traversing in this way, but you will observe that no node is being traversed twice. So G7 is G1, G5, G8, and G4. Likewise, if you talk about non-touching loops, so first we'll try to identify two or pairs of non-touching loop. So if you look at this figure, you'll see that this particular loop and this loop is non-touching. Likewise, you'll find that this loop and this loop is non-touching. Again, G7, G8, G4 is non-touching to G3. So we identified three pairs of non-touching loops, which are L1 and L2. So L1 is G9 and L1 and L3. So G9 and G3 are non-touching. We are talking about this loops. And again, you have L4 and L3. L4 is G7, G8, G4. So G7, G8, G4 is non-touching to G3. Likewise, you have third pair of loop L5 and L1. So L5 is G1, G2, G4. G1, G2, G4 is non-touching to G9. Now in this particular case, you don't have any three pairs of non-touching loop. So if you see, you got three pairs of non-touching loop, but you don't have three non-touching loops in this case. So you are going to substitute 0 for this particular expression when you face this in the expression of delta. And of course, if you find three non-touching loops to be 0, then further you're not going to observe or realize four non-touching or five non-touching loops, because they will automatically be 0. So if we are going to substitute these values into the expression of Mason's gain formula, that is transfer function. But before that, we are required to find the value of delta as well. So delta was given by the expression 1 minus sum of all loop gains plus the sum of gain products of two non-touching loops minus sum of gain product of three non-touching loops plus sum of gain product of four non-touching loops, and so on. So in this particular case, because you identified that there are no three non-touching loops, so this section goes to 0 and we are not going to talk about further. So now we are left with individual loops and pairs of two non-touching loops. So which means you're going to substitute the value of the loops for obtaining delta as 1 minus sum of loop gains. So this becomes the sum of loop gains, all the individual loops which were identified in this case. Then again, you're going to take the sum of gain products of two non-touching loops. So L1 and L3 were non-touching. So if you look at this case, L1 and L3 are non-touching, L4, L3 are non-touching, L5 and L1 are also non-touching, and thus we're going to multiply each of them, then add it in this expression. So we got L1, L3 added to L4, L3, then added to L5, L1. So this is the expression that corresponds to sum of product of two non-touching loops. And then again, you have sum of gain products of three non-touching loops to be 0, because there are no three non-touching loops in this case. Now again, we are now going to identify the value of delta 1 and delta 1, delta 2, delta 3. So we'll be having four deltas: delta 1, delta 2, delta 3, delta 4, and they will be identified using the forward path transfer function T1, T2, forward path gains T1, T2, T3, and T4. So let's write these forward path gains again. So corresponding to T1, if you are required to find, if you want to find delta 1 for T1, then as I told you yesterday, that you will have to eliminate the SFG that corresponds to T1 and the SFG that touches it. So if you look at this particular figure, the forward path T1 corresponds to the path starting from this point. So if I highlight this, so you start from this point, then move forward through G1, G2, then to the output side. So this was the forward path T1. So in order to find delta 1, I told you that you will have to observe the SFG which does not touches T1 and any part of SFG that does not touches T1. So you are going to eliminate T1, the forward path T1, as well as all the SFG which is directly in contact with T1. So if you observe that to this particular path, these SFG, the part of SFG in contact are this loop, this branch, this branch, and this branch. So the only SFG that you're left with is the G9. So let's redraw this G9 again. So I've taken this G9 out from the whole SFG because this G9 is the part of SFG which does not touches T1. Now for this particular case, if you are required to find the value of delta, so you are required to find value of delta which will become delta 1. So considering this as SFG, you are going to apply the same formula 1 minus sum of all loop gains plus sum of gain product of two non-touching loops. So in this particular SFG, you have only one loop. So there is only one loop, and hence you will be writing, or you will be getting delta 1 as 1 minus the sum of loop gain, since there is one loop G9, and thus this becomes 1 minus G9. Likewise, if we talk about delta 2, so delta 2 will correspond to the SFG which does not touches T2. So you identify T2 as G7, start from this point, G7, G8, and then to the output. So the SFG that doesn't touches this particular forward path is the loop G3. So you're left with only this part of SFG which doesn't touches the forward path T2. Otherwise, if you observe, you'll see that every part of SFG, for example, the branch corresponding to G9 to G5, G6, G1, G2, G4, they all are in direct contact with the path T2. The only branch that is not in contact with T2 is G3. So let's redraw this. So we are left with an SFG having only one loop starting from this as node and coming back to the same node which has its transmittance as G3. So delta 2 corresponding to this particular SFG comes out to be equal to 1 minus G3. Now if we talk about the forward path T3, so again if you try to identify the values of T3, what is T3? It's G1, G5, G8. So G1 starting from this point, G1, G5, G8. So if I highlight this, so this is the forward part T3. And now if we try to identify part of SFG which does not touches T3. So if you carefully observe the figure, you'll see that all the branches which are not part of T3 are in direct contact to it. So if you talk about G7, it is also in contact at this particular node as well as this node. G9 is also in contact, G5, G6 is also in contact, G2 also contacts, G3 is also contacts, G4 also contacts. So now you're not left with any part of SFG which is not in direct contact with T3, which means that if you find delta 3, you're left with one only. So since there is no SFG, thus no loop, and hence you are left with 0. Likewise, if you look at the forward path T4, so that is G7, G6, G2. So G7, G6, G2. So again, carefully observing, we see that there is no part of SFG which does not touches T4, and hence again you have delta 4 given as 1 minus 0. So now you obtain the value of delta, you obtain T1 through T4, then delta 1 through delta 4. So you are going to substitute these into the formula that you learn, the Mason's gain formula, which is given by summation delta k, tk delta k upon delta, and k varies from 1 to 4, and thus you got transfer function given as T1 delta 1 plus T2 delta 2 plus T3 delta 3 plus T4 delta 4 upon delta. And if you substitute these values and these values, you get in the numerator this. And if you're going to substitute delta as these values, so I have not substituted it in order to make it look simpler. So if you're going to write this in the examination, that will be fine. So it's understood that L1, L2 represents the gain that we obtained in this case here. Now if we talk about the second example, so our second example is a modeling of an automobile braking system. So suppose that you apply brakes, and these are the forces that are exerted on the left and right brakes. So F is the force that is exerted on, sorry, it's on the front wheel. So FF corresponds to the force being exerted on the braking force exerted on front wheel, and FR is the braking force that is exerted on the rear wheel. And the input is given through the, if it is two-wheeler, you're going to apply in the form of clutch as input, and if it is a four-wheeler, then you will be applying brakes close to the throttle. So this is a simple modeling of a brake system that you have in automobiles. It's a four-wheel or anti-lock automobile braking system. It uses electronic feedback to control the brake force on each wheel automatically. A block diagram model of a brake control system is shown in figure. FF and FR are the braking force of the front and rear wheels. RS is the desired automobile response on icy road. So this is the desired response on icy road. So you're required to find the transfer function FF by R. So since you see that in this particular case you have one input but two outputs, and as I told you that if you talk about transfer function is the ratio of output to input, which means that you will be dealing with only one output, not two. In this particular case, since you have two outputs, so and the question says you to find the ratio between FF and R, and thus you are going to forget about FR. So you are not going to look for FR anymore, because in the question it's talking only about FF as output, and thus you will be looking this as output and this as input. So you will be trying to find the ratio between this output and this input only. So you can apply block diagram reduction technique to this problem, as well as if you apply, because in the question it's not written to apply block diagram reduction or SFG, and thus I suggest that you prefer SFG because the solution will be simpler and straightforward. So let's try to draw its SFG. So this is the redrawn model, and if we draw the SFG of this particular block diagram, it looks something like this. So corresponding to RS, you have input here as RS, then you have the summation point given by the node here, then you have this particular point represented by this node here, and this node is given by this particular point is given by this node, and this takeoff point is given by this node. Now again, since you have only one output in this case, thus you will be assuming that the output is taken from this side, and you are not going to forget about this point. So there is no need to take care of this point. You forget about it. The only thing that you require is the ratio between RR and FF. So if you're going to simplify this SFG, you have to identify the forward path between the input and the output FF. So if you look at carefully to this SFG, you see that the forward path is starting from point G1, G2. So this is the only forward path in this particular case, while there is no other forward path that we'll observe starting from RR to FF. So let's write the first forward path, or you're only having one forward path, that is G1, G2. Now we move towards finding the loops. So loops in this case are given by, if you observe, you start from this point, move towards this node, then this node, and always move in the direction of branch arrows. So you come to this point. So this is loop 1. So let's write its transmittance. So it's given by G1, G2 minus H1. And the loop gain for second loop, if you see, you have another loop in this manner. So this is the second loop, and the loop gain corresponds to G1, G3 minus H2. Apart from these two loops, there is no other loop, and thus, and if you see that there are these two loops in the case, and they are not non-touching, so they are touching each other, and thus for the expression of two non-touching loop, you have 0, and then you find delta. Delta is given by 1 minus sum of all loop gains plus sum of gain product of two non-touching loops, and in this case the two non-touching loop corresponds to 0, and thus you get delta as 1 minus L1 plus L2 only, which is given by this particular expression. Now if you find, because you have one forward path, you will have to find the value of delta 1 to be used in the formula of Mason's, and thus delta 1 is 1 minus 0, because if you look at the forward path that you saw here, so this forward path will have no part of SFG not touching to it. So every part of SFG or branch or node, anything you will observe in this particular SFG will be touching the forward path. So this branch is also touching, this branch is also touching, this branch is also touching. There is a node which is not touching. So this particular node does not touches the SFG. But since it is only a point or a node, so for this particular node you don't have any loop, and thus there is no loop, and you will be getting an expression 0 here, and you get delta 1 as 1 only. If you are going to substitute this into the expression of transfer function, which is t1 delta 1 by delta, so t1 is obtained as g1 and g2. So if you are going to substitute this in place of t1, delta 1 is 1 and delta is given by this expression. So substituting this gives you the required transfer function of the given system. If you try to find the same transfer function between R and FF using block diagram reduction technique, then you will be reaching the same answer. So I leave this up to you. If you feel to confirm the answer, verify it using block diagram reduction technique, you can do it. So it's a good practice. If you like, you can apply block diagram reduction to this particular problem to look for the transfer function. Similarly, if it would have been asked about finding the transfer function, assuming that the output is FR instead of FF, in that case you would have been assuming this as output and will have been moving accordingly. So the transfer function would have been close to this value. In place of G2 you would have gotten G3, and in place of G3 it would be G2, and in place of H1 it would be H2, and in place of H2 it would come out to be H1. Again, another problem. So suppose that you this problem has different notions. For example, in this particular case you have two inputs. So in the previous problem we had two outputs while there was one input provided, while in this particular case we have one output and two inputs. So R1 and R2 are inputs, and it is required to find the transfer function when only R1 is applied as input and C is taken as output. In fact, you can find the transfer function if both the inputs are being applied, but you will have to find the transfer function with respect to only one input only. So as I told you, the transfer function is something that deals with only one output and one input, and that is why you will be finding transfer function which is only specific to one output and one input. So if it is asked which input are you going to consider, then you will be eliminating the second input. So first of all, let's because it says that we are desired to find the transfer function using Mason's main formula, and thus we'll try to first obtain the SFG of this case, and thus the SFG looks something like this. So you have R1. You first represent all the comparators, summation points, and the takeoff point by nodes. So corresponding to this comparator, you have this particular node. Then again, this comparator corresponds to this node. Then you have a comparator followed by a takeoff point. So they both will be represented by a common node. But if the takeoff point precedes a comparator, then they will be represented by a different node, and that is why this comparator is having a different node over here. And again, a takeoff point which is represented by this node. So first of all, you will have to draw all the nodes corresponding to the given block diagram. Then after drawing the nodes, you will be representing the branch arrows in the same direction as that originally given in the block diagram, and you will be assigning transmittance to each of these branch arrows. So if we have G1, the transmittance G1 is assigned, then you have G2 here, then you have H3 with a negative feedback. So since there is a minus sign over here, that is why I have written here a minus H3. Likewise, you have H2 which is having a negative feedback, and that is why you have a minus sign, and again minus sign here. And then G3 and R2 and R1 are inputs. Now since you are required to find transfer function, which will be always between the one input and one output. And in this case, you are desired to find the transfer function between R1 and C, and thus we are going to eliminate this particular input. We will only be talking about the relation between C and R1. So let's redraw this SFG after eliminating R2. So we are left with this SFG. So we eliminated R2, and now this particular node has no value. You can even eliminate this node as well. So you will be having only one straight branch with transmittance 1 and G3. That becomes 1 multiplied by G3. So this branch will be having a transmittance G3. So it's not necessary that you represent, because this node is insignificant. So that is why you can eliminate it. So since it doesn't have any other input coming or any output going from it, so that becomes insignificant. Now if we apply the Mason's gain formula, so before applying Mason's gain, we will identify the number of forward paths. So let's talk about the forward paths. In this case are G1, G2, this is 1. So this value, the gain of this branch will be 1, because this is 1 because you saw that there was no gain connected between this takeoff point and this summation point. Since there is no gain connected, and thus this will be having a gain or transmittance of 1, which is again represented in this case here. So the first forward path comes out to be equal to G1, G2, G3, which is between R1 and C. So take this output, and this has input. And I don't see any other forward path in this case, because if you say that this could be a forward path, so this is not possible because you have a branch arrow in the reverse direction. So that is why this will not be taken as forward path. So this is not a forward path. So you are always bound to move in the direction of branch arrows. Now we talk about loops. So in this case, you have how many loops? So I observe 3 loops in this case. One is G2 minus H3. The second loop is 1 multiplied by G3 minus H2. So G3 minus H2. The third loop is G1, G2, G3 minus H1. So these are the 3 loops that we obtain from this SFG. And if we now talk about the 2 non-touching loops, so in this case you don't have any pair of loops that are non-touching, and thus this gives a value 0. Now if you are going to substitute, before substituting we have to find the value of delta. So delta is given by 1 minus sum of all loop gains plus sum of gain product of 2 non-touching loops minus sum of gain product of 3 non-touching loops. Since you don't have any 2 pair of non-touching loops, and thus you will be left with 1 minus sum of all gains. Substituting these values gives you 1 minus L1 plus L2 plus L3, and this can be simplified and written in this form. And if you're going to substitute this into the expression, now delta 1. So we talk about delta 1. Delta 1 will be coming from the forward path T1. So if you look at this particular forward path starting from R1 till C, so this is forward path T1. So you see that there is no part of SFG that does not touches T1. So every part of SFG that you're left with apart from forward path is touching T1. So this branch touches T1. This branch also touches T1, and this branch also touches T1. So you're not left with any part of SFG that does not touches T1. And thus, if you apply the same formula, delta, which will become delta 1, is 1 minus sum of loop gain, since you're not left with any SFG, and thus this becomes 0. And this is what I have written here. Delta 1 is 1 minus 0. Now if we substitute each of these values into the expression of transfer function given by Mason's, so since you have only one forward path, and thus you have in numerator T1 delta 1 divided by delta, and this is the required one. So I guess that this clears you the application of the the Mason's gain formula. And if in case if you have any doubt or queries, you can ask me questions now as well as later on. So you can